All right, Unit 8, construct a linear equation giving a real-world context. So we're going to go back to, we've looked at equations on graphs, we've looked at the different forms of equations, and we've defined variables for these equations. So now we're going to construct these linear equations. And I think we've started to do this, and so I think it'll be a fairly easy transition for us. So let's we're just going to look at those examples that were back in Learning Target 6 and that we defined variables for. So we were looking at Stacy, and she was selling bracelets to help her support her favorite cause. She bought a box of bracelets for $15. She sells bracelets for $2 each. So we decided her independent variable was going to be bracelets sold, and her dependent variable was going to be money raised. So the number of bracelets she sold affected the amount of money she raised. And then we also decided that, or we didn't decide anything else than that. Now we need to make an equation, okay? So we gotta think about two things. We gotta think about our y-intercept in this case and our slope. So y-intercept can also be said starting value, startup cost, starting something. So take a guess here. What's our y-intercept? What does Stacy start with? What's her beginning situation here? Well, I'm seeing that she buys a box of bracelets, okay, for $15. So that means I'm seeing here that this is a negative $15. She went in the hole $15. If we're talking about money raised, she just unraised a bunch of money, right? She just spent a bunch of money, okay? And then what's her slope? Well, she's gaining money at $2 a rate. So this would be our slope. This would be our rate of change. This is our rate of profit, all right? So if we put that in an equation then, we can say, and sometimes it makes sense in these world problems to say, okay, she started with negative $15, but she's getting $2 for every X or for every bracelet she sold, okay? And if you want to, you can say she starts with negative $15 and she gets $2 for every bracelet she sold, okay? So this is fine. This is equivalent. Best math practice says that we should write 2x minus 15. But I feel like this makes more sense in the problem. So either way is fine when you're talking about problems. All right. A minivan, if you guys remember the minivan, is 220 miles from its destination of Flint. So here's Flint, here's the minivan, and it begins traveling towards Flint at 72 miles per hour. Okay. We decided our independent variable, time doesn't change, and our dependent variable was distance in miles. Okay, so let's pick out our two, our slope and our y-intercept here. Slope and y-intercept, which one is which? Take a guess. Well, first key is this miles per hour. Anytime you see the per, anytime you see a slash, that's your slope. He's going 72 miles per hour. All right, but let's first talk about our y-intercept. It's starting 200 miles away from its destination. So this is our starting point, right? So if we have an equation here, we're starting at 220 miles. Now, we're getting closer to Flint. So we're taking off of that starting point, right? So our slope is going to be negative. We're coming 72 miles closer per hour, where x is hours, y is time, or x is time, yeah, so x is hours and y is distance in miles. Now, you could think of this as, if you wanted to, negative 220 miles plus 72. So if you're saying it's starting negative distance away and coming closer, that's the same thing, but one of these has to be positive and one of these has to be negative because we're closing the gap. And so when y is 0, that means she's arrived at Flint. And if you come from the negative or the positive, it doesn't really make sense, or it doesn't really matter. This one just makes more sense to me, and of course, best math practice would say we write that as y equals negative 72x plus 220. And again, if you wanted to use hours and distance here, if you wanted to use different variables, that's fine as well. Final example here. Example C, Devin is going on the carnival rides, and remember she had $20. She wants to ride Ferris wheels and zip lines. The Ferris wheel cost $2, the zip line was more expensive, cost $4. Our variables here, remember, were not independent and dependent. They weren't money because the money was fixed. It's $20, $2, and $4. Those don't change. They're not variables. So the variables were how many times we're going to ride the Ferris wheel, how many times are we going to ride the zip line. So let's start with her constant. Since we know this one's not going to be a y equals mx plus b, it's going to be in standard form. What's her constant? Well, she has $20, right? So $20 equals, and she could either spend, or for the zip line, let's make the zip line x, or the Ferris wheel, I'm sorry, let's make the Ferris wheel x. So for all the Ferris wheels, she's going to spend $2. So $2 for each x ride. Plus, she's going to spend $4 on each zip line ride. All right. And so here, this is where we can talk about, well, she could spend a lot of money. If she rides the Ferris wheel 0 times, she could ride the, if she rides the zip line 0 times, she could ride the Ferris wheel 10 times. If she rides the zip line 0 times, she could ride the Ferris wheel 5 times. Other way around, I'm sorry. But there's going to be lots of different scenarios here. And then later in the year, we'll get to where maybe she has a different stipulation. We can find out exactly what she has, okay? Before class, you're asked to consider this following scenario. Sam has already burned 325 calories before he swims. He begins to swim for his workout. His swim will burn 7.8 calories per minute. Check out that per. You're asked to define variables. That's step 1. So go ahead and write, what are my 2 variables? Are they independent and dependent? And then write an equation in slope-intercept form, okay? And then explain what each part of your equation means in terms of Sam's situation, okay? So that's what you're asked to do before class.